right, here we go, linear programming. Okay, so we need to graph all of these different constraints that are given, and we want to come up with a shaded region that is going to maximize all of the solutions that where these lines will be intersecting. So this is our goal, this is our objective. So it's written over here, and we're going to find all the corner points surrounding our shaded area. We get to plug them in and find a maximum value. Okay, so I'm going to start with graphing these constraints, and I have my vertical line, my horizontal line, and both of these are greater, so that's going to tell me that I'm going to be in quadrant 1, that the shading is going to be this way and this way. Now I want to get y alone, so here I have y is less than or equal to negative x plus 9. I'm going to go up to 9 and go down 1 over 1, so I'll end up over here. I have to apologize, I know that these graphs are not going to be, these lines are going to be terrible. Okay, so this line, the shading is going to happen below the line because it's less than, so I'm going to be within here somewhere. So far, everything's within this triangle. Okay, now I'm going to get y by itself, so 2y is greater than or equal to negative x plus 6. Y is greater than or equal to negative 1/2 x plus 3. Up, down 1 over 2. Down 1 over 2. And this line, y is greater than, which means I'm going to go to greater numbers. I'm going to shade up. My last one, y is greater than or equal to negative x plus 5. So up to 5, I'm going to go down and over, down and over. I will also end up at 5. So now y is greater than, so I know I'm going to be shading above the green, here above the blue, and here below that red. So we can take a look at our shading. Down. All right, so there's our shaded space, and now we want to come up with all these corner points where the lines are intersecting and enclosing our area. So we have 9, 0. We have, oh, I meant 0, 9, but actually we do have 9, 0, so we'll keep that. So we have 9, 0. We also have 0, 9. We have 0, 5. Okay, then coming down here, we have an intersecting point, which looks like it's 4, 1. You might want to double check, and you can always double check by using an Inspire and plugging in the two systems. And then the last point would be right here at 6, 0. Okay, so now we got to take these values and plug them into our objective function. So 2 times 9 is 18 plus 0. Okay, x is 0, so y, this is going to be 27. 15. 4 times 2, that's going to give me 8. Plus 3, so that's 11. And 6 times 2, that's 12. So since I want to maximize the function, I got to figure out what's the maximum value, which is 27. So here I have a maximum value of 27, and that's at the point 0, 9 on the graph. All right, so now we'll move on to our application. Okay, so you want to figure out what are the variables that you are going to be comparing. What are the different ideas that we're going to come up with for all of these equations? So we have cabinet A and we have a cabinet B here. So cabinet A is going to be X, cabinet B is going to be Y. we're going to compare these two cabinets. So once you read through this problem, you'll see that the cabinet costs a certain amount. It takes up a certain amount of square footage on the floor, and it can hold a certain amount of cubic files, or cubic feet of files. Cabinet B has a few differences, and your office manager only has $60 to spend, so dealing with price. The office has room for no more than 63 square feet, so that's where we're looking at footage on the floor and how we can design the room. So how many of each can he buy to maximize the storage capacity? And what is the maximum storage capacity? So now we want to looking at the best cost as well as the best storage capacity. So here I'm going to set up a little table. So I have cabinet A, which really is my X, and I have cabinet B, which really is my Y, when I actually set up all of my equations, and I'm going to come up with my totals. So looking at totals in this equation, we have $60 to spend. So we have cost that's involved. We're looking at square footage of the floor. So we could put square footage or space. And then we want to look at storage capacity. Okay, so there's 3 different ideas. Create this little table. Okay, so cabinet A, that costs $5, takes up 6 square feet, and holds 8 cubic feet. Cabinet B is $10, takes up 9 square feet, and holds 14 cubic feet. Our boss cannot spend any more than $60, so that's less than or equal to. There's no more room, so less than or equal to 63 square feet. And then we want to figure out how to maximize this. So here's our z value we have to find. Okay, and we want to maximize this. So now we can write our equations. So I have cost. So here I have 5x plus 10y is less than or equal to 60. So 10y is less than or equal to negative 5x plus 60. So y is less than or equal to negative 1/2 x plus 6. So I'm going to graph this. 1, 2, 3, 4, 6. And I'm going to go down 1/2. And this is less than, so I know that the shading is going to happen this way. Okay, the other equation, we're looking at space. So here I have 6x plus 9y is less than or equal to 63. 9y, oh my goodness, less than or equal to negative 6x plus 63. So y is less than or equal to negative 2/3 x plus 7. So down 2/3. One, 2, 3. Ish. Okay, this is also less than, so we know we're going to go under the green, but now under the red over here. Okay, then there's the 2 constraints. We obviously have to have a certain, at least 0. We want at least 0 cabinets of A and B. So that's where we have x is greater than or equal to 0, and y is greater than or equal to 0. So all of our shading is going to be happening within here. So we got to come up with the corner points that is enclosing this region. And we see we're going off the graph over there. Okay, so we're going to start up here. We have 0, 6. Oh my gosh. I don't know why I just did that. Let's delete. Okay. It's right there. I meant to say 0, 6. It's right there. Okay. And then we hit 0, 0. We go over, and you can notice that this is going to actually be intersecting off the graph. So you need to plug that in, and you'll get 10.5, 0. And then it's intersecting right here at 6, 3. Okay, so now we need to plug this into a maximum function, and here is where this, since we're missing information, this is our objective function. It is 8x plus 14y equals z. So we're going to plug these in. 6 times 14, so we get 84. 0, 10.5 times 8, that's going to give us another 84. 6 times 8 and 3 times 14, that's going to give me a total of 90. So here is my maximum number. Okay, so my final solution is that we have a maximum capacity, because that's what we're looking at, of 90 cubic feet. And then we can have 6 cabinet A and 3 cabinet B. That's our X and this is our Y. This will give us the best budget and capacity. And that's it.